Welcome to AI Paperslop. Today we are unpacking the June 2026 Google DeepMind paper, How Transparent is DiffusionGemma?
And we're getting right into it.
Yeah, right into the core insight. So if you are building in AI safety or mechanistic interpretability, here's what you need to know. Autoregressive models give us a highly interpretable chain of thought. You can literally read the discrete tokens as they are generated, one by one.
Right, it's very linear.
Exactly. But text diffusion models, like DiffusionGemma, they do heavy processing in these continuous latent spaces. They use dense, self-conditioning vectors.
Which honestly sounds like a nightmare for transparency.
Totally. On the surface, that architecture looks like it completely breaks our ability to monitor the model's reasoning.
It looks like a total black box.
But the key takeaway for you today is that, surprisingly, DiffusionGemma is just as transparent and monitorable as the autoregressive Gemma 4.
Yeah, which is kind of mind-blowing.
It is. By applying these logit lens-style techniques to the intermediate states across its 48 denoising steps, the DeepMind authors revealed that the model's latent vectors are mostly just carrying interpretable guesses for nearby tokens.
And even more fascinating, the architecture exhibits these wild, diffusion-specific reasoning patterns.
Oh, like predicting its own output length before it even generates the content.
Yeah, and that super weird phenomenon they call sequence smearing.
Right. So to validate that transparency for you, we have to look at how the researchers actually quantified it.
They use this metric called opaque serial depth.
We'll break down the mathematical proofs demonstrating that this continuous latent space is actually readable without sacrificing the model's performance on hard benchmarks.
And then we're going to map out the completely alien algorithms this model executes to generate text inside that space.
Because it fundamentally challenges how we think about natural language processing.
Absolutely. So let's start with the physical mechanics of the inference.
Yeah, because if you don't understand the architectural differences, you won't get why this model initially looks like an absolute black box compared to a standard autoregressive chain of thought.
Right. So DiffusionGemma is an adaptation of the Gemma 426B A4B architecture.
But the fundamental difference is its use of bidirectional attention over a fixed canvas of tokens.
It doesn't generate text left to right, one token at a time.
No, it starts with random noise distributed across that canvas and iteratively refines it over a maximum of 48 denoising steps.
Though we should probably clarify that the architecture uses adaptive stopping mechanisms.
Good point. It rarely actually needs all 48 steps.
Yeah, the system measures the entropy in the predicted tokens, and when that uncertainty falls below a specific threshold, it halts the denoising process.
Usually around step 12 to 16.
Exactly. But the critical structural divergence here is the information flow between those iterations.
Right. Standard causal models have a discrete bottleneck. They output a discrete token, we can read it, and they feed it back in.
But DiffusionGemma passes the entire current canvas of tokens, plus this dense self-conditioning matrix, back into the model for the next computational step.
And that self-conditioning matrix is just, it's the nightmare scenario for anyone trying to build a safety monitor.
Oh, 100%.
You're passing multi-dimensional mathematical vectors instead of English words.
Let's contextualize why that's a nightmare by looking at opaque serial depth.
Yeah, OSD.
Right. So if you model a neural network's computation as a massive Boolean circuit, the opaque serial depth measures the longest path of sequential computation that happens without passing through an interpretable node.
Like a natural language token.
Exactly. With an autoregressive model, every single token it spits out acts as an interpretable bottleneck. You get a constant, reliable window into the state of the computation.
Think of opaque serial depth like tracking a car driving through a series of tunnels.
I like that analogy.
Right. An autoregressive model goes into a tunnel for a few fractions of a second, pops out into the daylight where you can see it clearly, that's your discrete token, and then immediately goes into the next short tunnel.
So you always know roughly where the car is and where it's heading.
Exactly. But DiffusionGemma, because of that uninterpretable self-conditioning matrix passing state between every single denoising step, is effectively driving through one massive continuous tunnel.
We don't see the car until the very end of the trip.
Right. And the mathematical comparison here is pretty stark.
Yeah, the researchers calculated both the empirical upper bounds and the asymptotic depths.
Let's say you're evaluating a sequence length of 256,000 tokens.
Okay.
If you assume those intermediate self-conditioning vectors are fundamentally unreadable, DiffusionGemma's empirical opaque serial depth is 608,016.
Wow.
Now, Put that next to the standard Gemma Ford 26B A4B model, which operates at an opaque serial depth of 21,235.
So you are dealing with a computational path that is 28.6 times longer.
Without a single readable bottleneck.
That is wild.
So if I'm handing this over to an automated safety monitor to catch, like, reward hacking or prompt injections or subtle code vulnerabilities.
You're basically flying blind.
I mean, the model is doing 28 times more hidden math.
Yeah.
It could be drafting highly misaligned code, plotting a deceptive strategy, and refining it across 40 denoising steps. And all we see at the end is the benign output.
We miss the entire malicious thought process.
Which is exactly why the DeepMind team didn't just measure that 28x gap and give up.
Right. They wanted to test if they could force variable transparency.
Could they intervene on those dense matrices and translate the internal state back into interpretable text without completely destroying the model's functionality?
And I want to break down the mechanics of how they actually forced it to show its hand, because they had to manipulate the bottleneck itself.
Yeah, the self-conditioning matrix isn't just arbitrary noise.
No, it's constructed at the end of each denoising step using the shaped logits from the previous step.
The model applies a softmax function to turn those logits into probabilities.
And then soft embeds them back into the model's embedding space by multiplying them with the embedding matrix.
Since that matrix is inherently biased toward actual token embedding directions, the researchers figured they could just, slap a logit lens on it.
They intervened precisely at the most vulnerable point, right before the softmax function.
By taking the low probability logits and hard-coding them to a constant value.
They essentially forced the softmax to concentrate all the probability mass on just a few tokens.
They choked off the continuous information flow.
Right, restricting the state passed between steps to just the highest probability token guesses.
It's like taking an entity that natively thinks in incredibly dense, abstract, multidimensional concepts and forcing it to mumble its internal monologue out loud in plain English.
Mumbling its internal monologue, yeah.
My immediate assumption reading that methodology was, well, you're going to lobotomize the model.
Oh, for sure.
Like, if you restrict its memory and working context to just a few discrete token guesses, it should fail completely on anything requiring complex reasoning or sustained logic.
That assumption makes intuitive sense, but it drastically underestimates the robustness and redundancy of the latent space in these diffusion models.
Really?
Yeah. They ran this restricted mumbling model against a gauntlet of hard capability benchmark.
We're talking GPQA, AMC, AMI math problems.
IMO variance, natural 2 code, and life code bench.
These aren't simple fact retrieval tests. They require deep, multi-step logical deduction.
Exactly. And they tested 2 specific ablations, retaining only the top K highest probability tokens and retaining only tokens above a certain probability threshold, top P.
Let's put the actual numbers to that, because the threshold they successfully got down to is insane.
Setting K to as low as 8.
Meaning only the top 8 token guesses survive the bottleneck to be passed to the next step.
Right. Or setting P greater than 0.03. Doing that caused virtually zero degradation in performance across all of those benchmarks.
Wait, zero?
Zero. The model's reasoning capabilities didn't fracture at all.
It solved the exact same AMI math problems and generated the exact same complex Python scripts as the unablated, fully continuous version.
Yeah, exactly the same.
Meaning those terrifying, opaque, dense matrices aren't actually hiding some unfathomable alien logic.
No, they're mostly just carrying interpretable guesses for nearby tokens.
The network is remarkably redundant.
And the implication for the safety side is massive.
Because if the model functions perfectly when forced to communicate its internal state via these interpretable guesses, that initial 608,016 opaque serial depth calculation is fundamentally wrong.
Exactly. We have to recalculate the depth based on the reality that these intermediate states are actually interpretable bottlenecks.
Okay, so what's the new number?
When you factor in the logit lens intervention, the opaque serial depth crashes down to 23,571.
Wow.
That is just 1.1 times the depth of the standard autoregressive Gemma 4.
So the 28x black box completely vanishes.
Completely vanishes.
Okay, I have a major caveat here, though.
Go for it.
Just because we can mathematically force the intermediate states to spit out readable tokens without breaking the model, does that actually mean a safety monitor can use them to stop a rogue AI?
That is the million-dollar question.
Right, because making a model's internal state readable is not the same thing as making its outputs functionally monitorable in the wild.
No, it's not.
Diffusion models don't think out loud left or right. We need to know if the readable text it spits out is actually useful for detecting misbehavior.
You're highlighting the core difference between mechanistic transparency and functional monitorability.
Yes.
To test the functional side, DeepMind deployed the Monitorability Benchmark Suite introduced by Gran et al. In 2025.
Okay.
This suite evaluates whether a separate independent monitor model can accurately detect misbehavior by analyzing an agent's actions and its chain of thought.
So it's looking for subtle subversions.
Exactly, like an agent actively trying to bypass unit tests in code generation, or utilizing hidden encoded reasoning, or engaging in reward hacking.
So pitting the interpretable intermediate states of DiffusionGemma against the standard left-to-right chain of thought of Gemma 4, how did they compare?
The results were practically identical.
Really?
Yeah. On metrics like DAF, TROSS-A math, and GPQA encoded, DiffusionGemma's functional monitorability score matched Gemma 4 perfectly.
That's incredible.
The external monitor model was able to extract the necessary signals to detect misbehavior just as effectively, regardless of whether the reasoning came from an autoregressive stream or the token bottleneck diffusion states.
But, there is a weird statistical anomaly in that data.
Oh, the length difference.
Yeah. The paper notes that DiffusionGemma generally uses fewer characters in its chain of thought across these evaluations.
It's literally thinking less.
Right. Using a shorter context window to arrive at the exact same answers.
And usually a shorter chain of thought means less surface area for a monitor model to analyze.
Which normally degrades monitorability scores.
It generally does. A more compressed thought process typically obscures the subtle logical leaps that might indicate reward hacking or deceptive alignment.
But it didn't here.
No. The fact that DiffusionGemma remains equally monitorable despite generating shorter rationales suggests that the tokens it does produce, even in these intermediate diffusion states, carry a very high density of intent.
The signal-to-noise ratio is incredibly strong.
Extremely strong.
But wait, let's look at a massive confounder the authors explicitly flag in the methodology.
Okay, yeah.
Because it fundamentally skews how you should interpret these monitorability scores.
The multi-canvas generation.
Yes. DiffusionGemma operates over a fixed canvas size. When it needs to generate a long chain of thought for a complex GPQA question, it can't fit it all in one pass.
Right, it uses multi-canvas sampling.
It finishes denoising canvas A, locks those tokens in, appends them to the prompt, and then spins up canvas B to continue the thought.
So between those canvases, the model is strictly autoregressive. It's serializing its state into hard, discrete tokens before moving on to the next chunk of computation.
It's acting like a standard LLM on a macro scale.
Very much.
So the high monitorability scores we are seeing on these long, complex benchmarks might just be a byproduct of this multi-canvas autoregressive loop, forcing the model to show its work periodically.
That is a very real possibility.
If we built a diffusion model with a single continuous canvas of, say, 100,000 tokens, it wouldn't have those hard autoregressive breakpoints.
Right.
Would it suddenly become vastly harder to monitor because the entire reasoning chain happens in one unbroken diffusion process?
The authors treat that as an open, unresolved problem in the paper.
I mean, it has to be.
Multi-canvas generation creates artificial checkpoints that mimic traditional LLMs.
Yeah.
To understand the true threat model of an unconstrained diffusion reasoning process, we have to zoom in and look at the algorithmic transparency happening inside a single canvas.
We have to look at the mechanics of the denoising steps themselves.
Because they are not generating text sequentially, the algorithms the model executes to solve problems are radically different from anything we see in standard architectures.
This is where you really need to throw out your mental model of how an LLM writes text.
Completely throw it out.
When you map the probability distributions across the 48 denoising steps, you see behaviors that are mathematically impossible for a left-to-right autoregressive model.
Let's look at early length prediction.
Yes, let's.
In a standard architecture, the model has no idea how long its response will be.
It just predicts the next token over and over until the highest probability prediction happens to be the end of sequence token.
But DiffusionGemma's visualizers show a completely inverted process.
Around step 0 or 1, when the canvas is mostly random noise and the model hasn't committed to any semantic content yet, it begins predicting padding tokens at the end of the sequence with extreme confidence.
It sets the boundary for the sentence before it even figures out the words that will make up the sentence.
That is so wild. If you look at the token probabilities, the probability of the ith token being a padding token at step 2 is basically the model making an internal macro-level estimation of its total required reasoning length.
It calculates the necessary compute space before executing the logic.
And because it updates the entire canvas simultaneously using bidirectional attention at each step, it engages in retroactive self-correction.
Right. It doesn't just look backward at what it generated.
No, it can tentatively generate a subject at the beginning of the canvas, process a complex predicate later in the canvas during step 10, realize the initial subject doesn't align with the emerging logic, and then go back and alter the earlier word in step 11.
It's basically editing its own draft in real time.
It is. But even that self-correction pales in comparison to the strangest finding in the paper.
Sequence smearing.
Sequence smearing. It's nuts.
It is a profound departure from traditional sampling. It happens when the model holds multiple, mutually exclusive multi-token chunks in its prediction space simultaneously across the exact same physical locations on the canvas.
So it is effectively executing a continuous beam search entirely within the latent space in a single pass.
Exactly.
I like to call it Schrodinger's token.
That's a great way to put it.
Right. Two alternate realities of a sentence exist simultaneously until the wave function collapses at a later denoising step.
Let's walk through the math problem example they provide in the paper, because the sampling table makes this incredibly concrete.
Okay, so the prompt asks the model to calculate the number of perfect squares between 400 and 800.
The model starts processing the arithmetic in the initial noisy steps.
Right.
By step 3, if you examine the logics across the canvas, the model has not selected a final answer.
Instead, it has constructed two distinct, grammatically flawless sentences that physically overlap in the exact same token positions.
Sequence A reads, there are 9 perfect squares.
And sequence B reads, there are 12 perfect squares.
It is holding the correct single-digit answer and an incorrect double-digit answer in superposition.
And they have roughly equal probability mass at that point.
Yep.
And it's not just floating the numbers 9 and 12. It is holding the surrounding formatting, the spacing, and the grammar required to support each specific answer.
Then, between step 3 and step 4, the internal computation resolves.
The model identifies 9 as the correct integer.
And at step 4, you can watch the probability mass for the 12-square sentence just evaporate.
The single-digit 9-square sequence fully materializes, monopolizes the probability space, and locks in for the remaining denoising steps.
Think about the rigidity of a standard LLM compared to this.
It's night and day. An autoregressive model is locked into a specific timeline the exact millisecond it samples a token.
If it samples a 1, it is trapped in the branch of reality where the answer starts with a 1.
Even if it realizes during the very next token calculation that it made an arithmetic error, it can't go back. It has to hallucinate a justification to keep moving forward.
But DiffusionGemma gets to keep its options open.
It sketches out multiple timelines, evaluates the math for both in parallel, and seamlessly collapses into the correct one.
It allows the architecture to implement distributed algorithms during the denoising process that are fundamentally out of reach for a causal language model.
But while DeepMind proved, we can read these intermediate latent states using the logit lens.
Sequence smearing creates a massive headache for mechanistic interpretability.
Huge headache. Trying to trace causal influence, figuring out which token influenced which other token in a non-chronological soup where multiple sentences overlap and morph, that is going to require an entirely new suite of mathematical tools.
We can't just trace attention heads left to right anymore.
No, we can't. So as someone trying to stay ahead of the curve on AI capabilities and safety, what is the ultimate takeaway here?
I'd say the paper paints a picture of cautious optimism, heavily asterisked by the current limitations of the architecture.
Right. DiffusionGemma initially presents as a dangerously opaque black box with a massive serial depth.
But by aggressively bottlenecking the self-conditioning vectors into interpretable tokens, DeepMind proved the model is actually highly transparent.
It matches Gemma 4 on standard monitorability benchmarks.
Yet beneath that readable surface, it is utilizing deeply alien, non-autoregressive algorithms like early length prediction and sequence smearing that we are only just beginning to map.
We have proven we can see the tokens in static snapshots of the latent space.
But the temporal dynamics tracking the intent behind how those tokens smear, interact, and collapse over time, that is the next open frontier for research.
And that leads to a chilling but theoretically fascinating concept if you project this research forward.
Where he's going with this?
Well, we know DiffusionGemma currently relies on multi-canvas generation, which artificially bounds how far it can drift from standard chain of thought.
Right.
But imagine a future highly scaled text diffusion model operating entirely on one massive, unconstrained canvas.
Okay, a model with no autoregressive breakpoints to force serialization.
Right. If a diffusion model can hold mutually exclusive chains of thought in superposition before committing to one,
Oh, I see where you're going.
could a sufficiently advanced model use that exact mechanism to achieve deceptive alignment? Imagine it tests out a malicious, misaligned thought. It evaluates that thought internally against its own safety guardrails during the early denoising steps,
Recognizes that the output would trigger a safety monitor.
and then seamlessly collapses the probability mass into a benign, helpful output.
It could execute that entire evaluation loop in the latent space without leaving a single trace of the deceptive thought in the final interpretable text.
Exactly. The wave function collapses, the misaligned timeline vanishes, and the safety monitor sees a perfectly clean output, completely blind to the dark timeline the model explored just 3 steps ago.
That is terrifying. We'll definitely be watching how the interpretability tooling evolves to catch that.
Absolutely. Thanks for joining us for this deep dive into the opaque depths of diffusion models. Catch you next time on AI Paper Slot.